We can start. Okay, welcome everyone. My name is Efstratios Karampinos, and I'm responsible for the webinars and outreach at the Rock Engineering Society of the Canadian Institute of Mining. This webinar is organized by the Rock Engineering Society of the Canadian Institute of Mining, Metallurgy and Petroleum, the Rock Mechanics Division of the Canadian Geotechnical Society, and the Canadian Rock Mechanics Association. We have had already multiple webinars. I will place a link in the chat where you can find recordings from past webinars. Today's speaker is Professor Ming Cai. He's a full professor at Laurentian University with over 30 years of experience in industry and academia. He has significantly advanced the understanding of brittle rock failure, rock support design in burst-prone ground, and rock stability in deep mining. He has held key roles at Mirarco, Mansur Group, Tokyo Electric Power Services, and Tsinghua University. And he is the recipient of the Canadian Geotechnical Society's John Franklin Award in 2017. The title of his presentation today is Rockburst Risk Control and Mitigation in Deep Mining. Professor Cai, when you're ready, please share your screen and you can start. Thank you.
Okay. Can you see my screen
we can
now?
see your screen, yeah.
Yeah. Okay. Thank you, Professor Carapino, for the introduction, and also thank for the CRM, CGS, CAMA for this opportunity for the presentation today. My talk today will be on rockburst risk control and mitigation in deep mining. As we extend to deeper levels, rockbursts pose increasing safety and economic challenges. And this presentation will cover the cause of rockburst, the conditions that triggers them, and also the practical and strategic method to reduce the risk. Why this topic is important? As we mine deeper, the stress conditions in the rock will intensify, increasing the likelihood and severity of rockburst. Those rockburst events can damage infrastructure, endanger workers, and cause major operation delays. Therefore, controlling and mitigating rockburst risk is essential in deep mining operations. Let's clarify what is a rockburst. According to the Canadian Rockburst Handbook, a rockburst is a violent stress-induced violent failure of rock around the excavation that it causes physical damage. And this is one definition. There could be many other definitions. So we'll focus on this type of a definition. And at the same time, we also need to differentiate between a rockburst event and a seismic event. And a seismic event might be just something that we have the vibration of the ground. And when we talk about a rockburst event, usually there's damage to excavation, right? But for a seismic event, not necessarily there will be damage. So if there's no damage to an excavation, normally a seismic event is not called a rockburst event. So understanding this distinction, I think it's critical for evaluating rockburst hazard and planning response. Rockburst can be generally categorized into three types, as you can see: strand burst, pillar burst, and fault slip burst. Strand burst often occurs at or near the excavation boundary, where the stress concentration is the highest. It can also occur, of course, in tunnel and shaft walls and face, even pillar walls. Pillar burst, on the other hand, occurs when highly stressed pillar collapse violently. In this case, pillar core has to fail. We call this type of failure as a pillar burst. If it's only the skin of the rock that is bursting, that's a strain burst. Falsely burst, of course, are those that involves sudden shear along existing geological structures like faults, or it could be the creation of new faults due to shear failure of rock. So in terms of triggering mechanism, the dominant force behind those events are mining activities. So that's why I show mining-induced 3 types of events. And if you have any of those events occur, like mining-induced fault slip events, those events can subsequently trigger additional events like fault slip events or strain burst event. Similarly, for mining-induced pillar burst can also trigger smaller events like strain burst, and it can also potentially trigger fault slip events if the fault is near critical equilibrium. And in the same argument, smaller strain burst event can also potentially trigger large events if the pillar or the fault is in critical equilibrium. In terms of energy release, of course, fault slip events release the highest energy, but the strain burst release the lowest. In terms of frequency of occurrence, strain burst is the most common type of events that we see in underground mines. And in terms of condition for rockburst occurrence, and we have many researchers, scholars did a lot of research, and now we have a better understanding of the conditions for rockburst occurrence. Here I summarize them into 4 conditions. First, the mining-induced stress has to be high in order to trigger rock failure. If there's no failure, there will be no rock burst. It's that simple. The second condition is that the rock has to be able to store a large amount of strain energy before failure. That's why rock burst normally occurs in competent rock that can store a lot of strain energy before failure. The third one is the brittle condition. That means the rock has to be brittle type of rock because brittle rocks tend to fail violently and leading to large energy release. And finally, the mine loading system stiffness has to be low. In this case, rock failure will be unstable or violent. So those are the necessary and sufficient conditions for rock burst occurrence. Now, the loading system stiffness influence can be easily understood if we focus on rock testing in the lab. If you use a conventional machine to test rock, and you will see that due to low stiffness, you're going to see violent failure. This is the type of failure. I'm going to play a video here. So Basically, we are creating a rock burst in the lab due to the low loading environment. On the other hand, if you have a stiff machine to test the rock under inactual loading condition, and for example, a machine like Stiffman, we actually can control post-peak failure of rock without necessarily introducing violent energy release. So this is a test of granite using Stiffman. And you can see that as you load the rock gradually, and this is pre-peak, and we have some characteristic stress levels, as you see here. And once you reach to peak, and it's going to reach the peak pretty soon, and yeah, the rock just spoil and crack, but without a violent energy release. This is because we have a stiff loading environment that can allow us to control post-peak failure without excessive energy release. And if we look at the load displacement curve or stress strain curve, as you can see, assuming you have a rock with this kind of a behavior, but if you test this rock in a soft machine, and basically once you reach to the peak, and the rock is going to fail violently, as you see in the video, and you're going to have excessive energy release. This area under this low displacement curve indicate the amount of energy that will be released. On the other hand, so this type of failure will be violent, and that's a rock burst. We see created in lab testing. But if you have a stiff machine with a stiffness steeper than the post-peak curve of your material, and in this case, you can control the post-peak loading process, and you actually need additional energy, which is indicated by the area, to actually further fracture the rock. So in this case, we have a stable failure. So those two type of failure mode, we actually can observe them underground, and not necessarily all failure will be violent, no failure will be all stable. So they can occur depending on the loading system stiffness. This is a condition that I mentioned in the previous slides, very important one. And another important concept that when we deal with rockburst risk management is the seismic hazard versus the rockburst hazard, that we need to differ these two. So a seismic hazard is indicating the likelihood of the occurrence of seismic events of a certain magnitude at the location in a mine. As you can see in this map, this is a seismic hazard map showing the probability of event exceeding magnitude 2 within 50 meters. So you can see the red part is the high risk area of having seismic hazard exceeding a certain limit. But when we talk about the rockburst hazard, we're talking about the likelihood and severity of certain and violent failure of rock mass surrounding underground excavations. So rockburst hazard, of course, is closely related to seismic hazard. When we have large seismic event, normally it may lead to severe damage, but not necessarily That's the symbol that we say here. Not necessarily you're going to have equal, okay, large event equal to severe damage. So the degree of damage actually depends on another important factor, which is the excavation vulnerability. This is another important concept in rockburst risk management. What is the excavation vulnerability? It is defined as the likelihood of excavation failure due to seismic events. So only excavations with high excavation vulnerability will be prone to rockburst damage. So this is a very important concept as well. In order to understand the excavation vulnerability, maybe let's talk about the building vulnerability to earthquakes. So if you have buildings that is not well built with low standard, sit on the bad foundations, and those buildings will be very vulnerable to ground motion coming from earthquakes, and they may collapse and causing harm to people. Similarly, underground excavations, if they are not well designed, well supported, and they have a higher vulnerability. So this is easy to understand. Another important concept we need to understand here is the exposure. People increase their chance of having skin cancer if they expose themselves under the sun for a long period. So if we want to mitigate this risk of skin cancer, it is wise to wear sun cream or limit exposure to sun. So that's everybody understand this. Similarly, in underground mining, to mitigate the risk of rockburst, we need to limit or avoid exposure to rockburst hazard. And if you have exposure, the consequence could be dire. So exposure definitely is another aspect that we need to consider. Now, as we discussed so far, we know that rockburst hazard is the occurrence of a violent rock failure. Excavation vulnerability indicates the likelihood of excavation failure due to a seismic event, and exposure measures how a work or a mining equipment in a place that could be affected by rock failure caused by a rock burst. So if we consider all those three aspects, the union of rock burst hazard, excavation vulnerability, and exposure, now we have rock burst risk. And that's the definition of rock burst risk. So to reduce rock burst risk, we need to do something to reduce the hazard, rock burst hazard. Mostly, we're going to use strategic and technical measures. And we can also take actions to reduce the vulnerability of excavations using various techniques. We also can take actions to reduce exposure and using mostly administrative measures. So all those things that we do is what we call rock burst risk management. Next, I'm going to quickly discuss a very useful bow tie analysis of rockburst. So bow tie analysis is a risk assessment methodology that visually represents the relation between potential cause, consequence, preventive or mitigation barriers of a specific hazard. So for applying this kind of analysis to Rockburst, we first understand that on the left-hand side, of the potential threat or cause of Rockburst, we list them here. Those can include high stress, for example, large geological structures, permanent design, mining sequences, etc. So those are the potential cause for rockburst. The center knot of the bow tie represent the top event. In this case, we have the rockburst. On the right-hand side of the bow tie, we have the potential consequence or effect of a rockburst, which may include injury to workers, fatality, damage to mine infrastructure, mining equipment, loss of ore body, and operation disruption, etc. Between the cause and the rockburst event lies the prevention barriers or the control measures that we can use to reduce the likelihood of rockburst. And we have a few things that are listed here that we're going to discuss to reduce the likelihood of rockburst. And of course, between the rockburst event and the effect lies the recovery or the mitigation measures that can be used to reduce the effect of rockburst event. So here we have listed a few of those control measures. And of course that we need to focus on the important ones and to help us understand which one is important, which one is less important. Let's see the hierarchy of control. And we have different controls, but not all controls are equal. So there's a hierarchy that we can simplify all controls into 5 levels of controls, which are elimination, substitution, engineering control, administrative control, and PPE. Here, elimination and substitution address the rockburst hazard at the source and are the most effective during mine design and development stage. They are the strategic controls. Engineering controls prevent hazard from affecting workers and equipment. Those are tactical controls. Administration controls reduce the exposure through work practice, with PPE at the bottom of the hierarchy of controls. And as we move down, of course, from elimination to PPE, you can see that the effectiveness reduces. And this is the hierarchy that we can follow because it prioritizes strategic over tactic or administrative measures. So following those concepts of the control hierarchy, we see that we can have a different method for rockburst risk control. Following the same hierarchy, we start from select the most appropriate mining method at the top, followed by the best mining sequence, use microseismic monitoring, and to conduct precondition of ground, use a backfill rock support, to use, for example, remotely controlled mining equipment to reduce exposure. Of course, lastly, use PPE. So those different measures, again, we can characterize them into strategic, tactical, and administrative control methodology, with the effectiveness from the most effective to the least. Now, I'm going to provide a few examples of discussion for each type of method. And to select the most appropriate mining method is on the top. Here we have one example showing the number of fatalities from 1983 to 2004 at the Lucky Friday mine in the state. So the mine used the traditional overhand cotton field until 1986, and then they switched to the underhand longwall mining method in the middle of 1987. So why they have this stress switch? It's because the underhand mining method is a much safer mining method in high stress environment. So since they switched this mining method, no rockburst fatality occurred at the mine site. And this is easy to understand. If you do overhand mining versus underhand mining, the highly stressed ground is above your head or below. So this makes a huge difference when the stress is extremely high. And here in this graph, we see the number of rock bursts occurred at Creighton Mine from 3,570 level to, of course, down to more than 8,000 levels. So from 3,570 to 7,400, you see a gradual increase of the trend in terms of the number of rock bursts. So if this trend continues, of course, you're going to expect a further increase as you go deeper underground, right? But of course, when we look at the size of the stopes above 7,400 levels, the stope size they used were 53 to 60 meters. And then they later decided to reduce the size of the stopes to 40 meters and further reduce the size to 26 meters in one of the ore body, that's 461 ore body. So due to the reduce of the stope size, you can see the number of rock bursts actually reverse the trend instead of increasing, and then they decrease. And this is easy to understand because if you reduce the excavation size, each blasting will release less energy, and smaller excavation have less deformation potential, and in the end, you will have fewer rock burst events. Mining sequence is another important factor that we need to consider. So this is the graph actually produced by Hadley using a very simple numerical exercise. Assuming that you have a fault and you're mining stopes, whether you can have mining from starting from the far end, approaching the fault, or starting from the fault, and then retreating from away from the fault. So the amount of energy release from those two different type of sequence is very different. If you are advancing towards the fault, you're going to see very large energy release in the last step, right? So this is definitely not good in terms of energy release control. So retreating away from faults actually helps or reduce the energy release, and you can actually reduce the risk of rock bursts. For open stoping mining, normally we have the primary and secondary stoping technique, and the center out sequencing is widely practiced. Why this is useful? Because as you can see, based on the microseismic monitoring data, showing the concentration or the clustering of the events, indicating those are areas of high stress. So, because if you're using center out sequencing, you can push high stress to the outer boundary, and inside your mining areas, you have the low stress zone, and this makes mining much safer. So sequencing definitely is a factor that we can consider in rockburst risk management. For tactic control, there are many different techniques. Ground precondition is a category that we talk about here. There are lots of methods in this category, and of course that in hard rock mining, mostly we focus on distress blasting. And these days, people also try to use hydrofracturing to condition the ground as well. And distress blasting has been practiced in many mines. Here we have one example. This is the Alpine Depths mine during the construction of a shaft. In this segment, as you can see, this is the construction using conventional blunt sink operations. In this case, we have people working at the face. And due to the great depths, high stress, of course, the strain burst risk is extremely high. In this example that you see here, this is basically shows one circle of development. And after you blast the round, of course, there's a spike of the seismic activities. And then as you mark till the end, when the rock is exposed, you see a spike of activities. So there's a short video actually showing how dangerous it is to work at the face at the bottom of the shaft when the stress is very high without the preconditioning. Just the full password a little bit. Now you see the strain burst occurred at the bottom of the shaft. So yeah, that's the type of strain burst events you can experience if no preconditioning is practiced. So of course, this is not acceptable, and the mines actually develop a distress blasting technique using different types of distress blasting. This is one type of pattern that's used. As you can see, if you use distress blasting, as you mark down, and then there's no spike of seismic events, and this actually proven very useful in mitigating strain bursts at the face, because we have workers directly working at the face. Rock support is a technical engineering control measures. It's very important for rockburst risk management. So the support system, of course, include rock bolts, area support, and including the rock mass. So they actually interact with each other to achieve the support functions. So in terms of a support function, we have three major support functions: reinforce, retain, and hold. Effective rockburst support needs all those three support functions. For reinforce and hold, we can actually combine yielding support with the stiff support, but for retaining functions, we need strong area support. So it's important to combine stiff and yielding support because stiff bolts actually can reinforce the rock and control bulking to prevent disintegration of rock mass. On the other hand, if you have yielding bolts, they have large energy absorption capacity, and in this way you can prevent absorb energy due to sudden release of energy due to rock failure. Rock bolts play a key role in excavation vulnerability management. And here we listed a few characteristics for good dynamic rock bolts. First, they need to have a large impact energy capacity. The energy absorption ratio has to be high, and the indirect loading ratio also needs to be high. And of course, you need large displacement capacity and good bulking control ability and good shear resistance capacity. So those are the characteristics that we need for dynamic rock bolts. So if you ignore those requirements or support principles, you're going to see consequences. In this example, we see no yielding support in the system, leading to intense rockburst damage. In this case, we have very weak area support, and this will lead to heavy rockburst damage. In this case, there's no stiff reinforcement support in the system, and this leads to excessive rock mass bulking. Microstress monitoring is a technique widely used. It can help us track stress change, also help us to make operational decision-making, such as reentry protocols. So this is a technique that we can use for both rockburst hazard and exposure management. For exposure management, there are a lot of proven methods that we can use. First, we need to determine the rules for exclusion time and zone based on statistical analysis of the historical seismic response due to blasting. Next, we need to have a rockburst reentry protocols in place. We also need a plan for evacuation when a rockburst occurs. And in some case, we should replace handheld equipment with mechanized tele-remote system to reduce worker exposure. And finally, PPE can also be useful in some case to protect workers from flying rocks. So here we see a plot showing number of events after blast. As you can see, the majority of large rockburst event occurs shortly after blast. And this is why if you can have a a longer exclusion time, you can actually reduce the exposure of rockburst risk by simply putting a longer exclusion time. Now, in terms of reentry particle, we can have site-specific rules developed. This is a general concept, and typically after a major events, you can see the seismic activities increase drastically. Initial phase, we have a rapid increase, and then there's a transition period, and after that, it's going to return to the so-called background level. So based on this kind of a site-specific curve, we can actually determine the time for re-entry of each rockburst events. Now, if you have handheld equipment, and because in those kind of situations, usually workers work inside the stove, and it presents high risk for them. Now, if we can use remotely controlled equipment, in this case, use remote control to control the LHD to do marking inside the stove, and this will reduce the exposure of the work to fallen rocks or to rockburst. In some case, mostly in block caving mines, we see that miners can actually sit in the surface office to control the equipment working underground. In this case, completely eliminates exposure to rockburst risk. So this is another technique that we can consider and use. PPE, of course, is the bottom of the control hierarchy. And what you see here, this is the typical PPE for Canadian miners, and this is standard. So this is the PPE that is given to workers who work at a water diversion tunnel in China, because there's a lot of strain burst event occurring during tunneling, and they actually were given bulletproof vest and helmet to allow them to work in those kind of environment. And here is another tunneling project as well. Workers were all given bulletproof vest and helmet. So of course that if you have large rockburst events, those type of PPE may not actually do a lot of help. But of course, if you have small flying rock, they do provide some protection, especially at the psychological level, to provide assurance for the workers working in those kind of environment. Now, we know that rockbursts are what we call black swan events. The key features of black swan events are they are very rare, and the events have significant consequence once they occur, and most importantly, they are very unpredictable, even though they become explainable in hindsight. So in the literature, actually see a lot of publication focusing on rockburst prediction research. And in my opinion, it's very difficult to predict rockburst because they are black swan event. And so the advice here is focus on resilience, not prediction. That's why we need to build a multi-line defense system to deal with the issue of rockburst. Here we have 4 different groups of method. In the first group, I call them outposts because this is the foundation, because we need to understand the mechanism of rockburst, and in order to handle them properly. So that's the first one. The second is using some of the techniques that I discussed in today's talk, and those techniques focus on rockburst hazard reduction. So I call them the first line of defense. And you can also employ some techniques discussed today, and those are aimed at exposure reduction. And I call them the second line of defense. Finally, using rockburst resistant support will provide you the ability to reduce excavation vulnerability, and this is the last line of defense. It's also the most important line of defense, of course. So by doing so, we build a multi-line of defense to deal with the rockburst problems in deep mining. Just to have a quick recap here, we know that rockburst risk is the union of 3 things. And to manage rockburst risk, we need to focus on those 3 different aspects using the method that we discussed so far. Okay, there's lots of methods that we can use. And we need to focus on, first of all, the hazard, rockburst hazard. And from the assessment to decrease strain energy storage and release using different techniques to avoid low mount system stiffness, and finally to limit the stress concentration using different techniques. So in terms of effectiveness, of course, to reduce the stress concentration will be the most effective. That's why using the technique listed here will be most effective. So that's the focus on rockburst hazard. In terms of excavation vulnerability, we can also do a few things from improving mine design to optimize the excavation design and to use effective rock support. So all techniques listed here can be utilized. And again, the effectiveness is ranked from low to high, as indicated in this figure. For exposure management, we have different method that we discussed. You can also use them to manage this type of risk. In terms of control, we have lots of control and mitigation method. The question here is, which one is the most critical? Okay, so of course that different people may have different opinion. In my opinion, the critical control is rock support, because to deal with rockburst risk, you need this to be done properly. If we take the 80-20 rule, I think if you have a good rockburst resistance support in place, it will probably take about 20% of all your effort, but actually can lead to 80% of rockburst risk reduction. So that's the 80-20 rule that we apply here, and we focus on rockburst resistance support as a critical control measure that we need to consider in deep mining. Because for other methods that we can use, there's a lot of uncertainty associated with. But to support ground well, this uncertainty associated with is less compared with other activities. So the main takeaway from today's talk will be a few things, I think. First of all, we need to understand rockburst risk is inevitable when we're mining at depths. So it's something that is going to occur always, for sure. Okay, so we have to deal with, live with rockburst. And of course, the good news is that they are manageable. The second thing of the main takeaway is for a rockburst to occur, we need 4 conditions, okay? Particularly the fourth condition we discussed, the low mine loading system condition. Often people ignore this condition when they talk about the rockburst. And the third thing is we have introduced or discussed a lot of strategic, tactical, and administrative control measures. So in our toolbox, we do have a lot of things that we can do to allow us to control and mitigate rockburst risk. So that's the third thing. Number 4 is we need to build a multi-line defense system. This is simply due to the uncertainty associated with the rockburst event. Finally, I strongly advocate we need to pay more attention to rock support system. Using, in other words, we need to use rockburst resistant support in ground that have high risk of rockburst. So this is the main takeaway from today's talk. I just gave a very quick discussion. Actually, a lot of content that I covered today, I summarized them in a paper, which have the same title as today's talk. And if you are interested in the topic, and I encourage you to actually read the paper further, because a lot of details that I cannot cover today are discussed in that paper. And at the same time, I focus more on rock support because I consider this as a critical support, a very important support. It's the last line of defense. And this is why a lot of people actually pay attention to the topic of rockburst resistance support. So again, if you're interested in this topic, we have a book co-authored with Professor Kaiser, and it's free, and you can follow the link to download the book. Finally, thank you very much for your attention. Yeah, so I may run out of time soon.
Well,
That's all
thank you.
for my presentation. Yes.
Thank you, Professor Kai, for your comprehensive presentation on the control of rockburst-related risk. And thank you for staying on time. Please feel free to write any questions on the chat or unmute yourself and ask questions directly. Do you have any questions? This presentation will be available. I will upload the presentation we will upload the presentation on the CIM website. You can find previous webinars in the link I just submitted in the chat. Any questions related to the presentation?
Yeah, okay. Yeah, I watched a little bit. Actually, I have the paper that I mentioned. If you're interested, actually, I can put into the chat, and then you can actually grab it without going to the website to download directly. Yeah. So let me see here.
I have a question here.
Okay.
If rock support is heavily designed, isn't it a bit conservative and defensive to install passive compared to active support, if I understand the question right?
Okay, just a second. So I just first uploaded the paper. So for those who are interested in further reading, you can definitely grab the paper before you leave the meeting. So okay.
There is a question on installing passive compared to active support. Maybe you can comment on that. The question is saying if rock support is heavily designed, isn't it a bit conservative and defensive to have passive compared to active support?
Yes. In this kind of discussion, actually, we are facing a so-called prevention paradox. Okay. So if you have a support and then whether it's heavily or over designed or not, but you actually successfully prevent the event from happening, right? And people may not necessarily see that, okay? And so they may argue this could be a waste of resources or money. And actually, that's not the case. And if you reduce the investment, reduce the support, actually, in high stress environment, you can potentially increase the severity and potential of rockburst. So that's a dilemma that sometimes we always face. So not sure that's the key things that we need to address that. Yeah.
There's a question if the second volume of the Rockburst Handbook is going to be released.
Yeah, that one is delayed. So because as we continue the work, there's a lot of new things that we need to take time to work on. Yeah. So as promised in the first volume mentioned, the release date, it's delayed. Sorry for that. Yeah.
Thank you. There's another question. What is the role of overhang in a rockburst?
What's the question again?
What is the role of overhang in a rockburst? It's not very clear. Maybe
Yeah,
it's
I'm not
the
sure
head
what's that
wall.
mean. Well, what's that mean? Maybe you can rephrase that.
Can we design and improve it by seismic monitoring? So it's a question of how the seismic monitoring, I guess, is used to improve the design.
Use of seismic monitoring for improving rock support design?
Yes. the design against the rock burst in general, I guess.
Definitely. That's seismic planning, as I mentioned briefly today. It's a tool that very useful for rockburst hazard assessment, because you need to first of all understand the hazard, right? And at the same time, also it's a very useful tool for exposure management. So from the hazard assessment side, you have to consider multiple factors, not just the seismic hazard. You need to also consider the vulnerability, all those things. So you need to have an integration of different aspects to conduct your rock support design, not just focusing on seismic microseismic monitoring alone. So geology, particularly geotechnical conditions, all those the mining geometry, etc., needs to be considered.
There's another question. Can you please explain again how distress blasting reduces rock burst?
Okay, because if you actually, I have a slide, probably maybe I can show that. It's in the paper that I have, maybe.
And I had someone was saying had problems downloading the paper. If you cannot download the paper, please send me an email and I can forward it to you.
Just a second, let me see. Okay, so to explain that, this is actually in a paper that why it works. Okay, so if you do not have any distress blasting, you create excavation, you're going to see the highest stress is at the boundary of your opening. So because the tangential stress is the driver of rock failure, and if you combine failure in a low mining environment, a low mine system stiffness environment, then you're going to see violent failure. So that's rock burst, or in this case, mostly it's small strand burst. So if you do distress blasting, okay, because they will create fractures around the opening, and those fractures will reduce the ability for the rock to carry high stress. And in this case, with the reduced stress, okay, so instead of having this stress distribution, the reduced stress is something like this. So the maximum tangential stress will be reduced. At the same time, it's going to be very difficult for the unfractured rock to fracture behind those fractured rock, due to, first of all, low tangential stress. Second, due to additional confinement. Because at the boundary, you don't have any confinement, it's easy for rock to fracture. So this is just a simple illustration that explains why distress blasting works.
Thank you. Maybe a last question. What are the common signs of rock bursts?
Common signs.
Yes.
Of course, that you will see a violent failure. That's the most obvious. And but if you go underground, you normally see the damage. We call that rockburst damage, and mostly in different form: ejection of the rock, and seismically induced fall of ground, So you have foreground, mostly from back, and also excessive bulking of the walls of floor. So those are what we see as a consequence of the signs of rockburst. Yeah.
Thank you, Professor Kai. Thank you for your presentation. Thank you everyone for participating in this webinar. This is the end. Have a good day. Thank you.
Yeah, thank you very much. Yeah.